This is a mini tutorial on problem solving using kinematic equations and freefall. Okay, remember we learned in the last tutorial that freefall has a constant acceleration of 9.8 meters per second squared. And we can use this along with the kinematic equations, which I will go ahead and write down for reference purposes. Delta x equals v0 t plus 1/2 at squared. V equals v0 plus at, and v squared equals v0 squared plus 2a delta x. Okay, now it turns out that in freefall we can use the fact that the acceleration is always 9.8 meters per second squared to solve some problems that you otherwise might not be able to solve. For example, let's say we drop a rock off of a bridge, and it takes 1 second in order to hit the ground. Okay, so this rock lands 1 second later. So the question is, how tall is the bridge? So at first you might think, well, we don't have enough information to answer that question because after all, we're only given a time, and all of those kinematic equations have at least 3 and sometimes 4 variables. So how are we going to be able to solve a problem given only one piece of information? But actually there's some other information buried here in the statement of the problem that if you know what it is, you can use in order to solve the problem. For example, okay, well, let's write down the obvious first. The time taken by the rock is 1 second. But we also know the initial speed of the rock. After all, the rock is dropped, not thrown. So if the rock is dropped, that means its initial speed is going to be 0. And finally, since the rock is in free fall when it's falling off the bridge, the acceleration is 9.8 meters per second squared. So we have A equals 9.8 meters per second squared down. And we're looking for how tall the bridge is, which is delta x, the displacement of the rock between the bridge and the ground. Okay, so now it looks like, hey, we have enough information to solve this problem after all. In fact, it looks like the first kinematic equation will do the trick. Delta x is equal to v0 t plus 1/2 a t squared. So delta x is equal to 0 because v0 is 0 plus 1/2. The acceleration is 9.8 meters per second squared times 1 second squared. Delta x is equal to 4.9 meters because 1 second squared is 1. You have the seconds squared here cancel with the seconds squared there, and you're left just with meters. Let's do the reasonable check and make sure that this is okay. Now 4.9 meters, you're probably not used to thinking in meters, but a meter and a yard are about the same size. So when you're doing the reasonable check, saying a meter and a yard are equal to each other is good enough. So if this was 5 yards instead of about 5 meters, then that would be 15 feet. Well, I think roughly 15 feet. Would it take a rock 1 full second to fall 15 feet? Perhaps. I know that if I dropped a rock from, say, my own height of roughly 6 feet in the air, it wouldn't take a whole second to fall. So I think if it's going to take a full second to fall, it would have to be dropped from some distance higher than 6 feet, but probably not 100 feet or some huge number like that. So 15 feet, that sounds about right. I think we've passed the reasonable check. Well, while we're at it, let's go ahead and find what is the speed of the rock just before it hits the ground. So we'll use the same initial information, but this time what we're looking for is v, just before it hits. This time we could use either the second or third kinematic equation. I'll go with the second one. That one will make the algebra a little bit easier. We have v equals v0 plus at. So v is equal to 0 plus 9.8 meters per second squared times 1 second squared. Again, 1 squared is 1 times 9.8 is 9.8. Oops, that squared is not there. You don't need it at all. It's not time squared, it's just time. But 1 times 9.8 is still 9.8. And this time, this seconds cancels only one of those seconds, so we're left with units of meters per second. The speed of the rock just before it hits the ground will be 9.8 meters per second. Okay, I'm going to clear the slide and work another problem, so if you need a moment to look at this, you want to pause your recording, and when you're ready to look at the next example, you can go ahead. All right, let's do another example. This time, let's say that we're going to toss a rock straight up in the air with an initial speed of 3 meters per second. And it's going to go up and fall back down. And it lands 10 meters lower than where it started. Okay, so let's find the speed just before it hits, and also the time that it takes to land. So this problem is a little bit more complicated than the previous one because we're given an initial speed. Okay, so once again, the first thing you should do is write down all of the things that you know and the things that you want to know. So first of all, we have an initial speed of v0 is equal to 3 meters per second. And the acceleration, because we're in free fall, is 9.8 meters per second squared down. Now here is somewhere we have to be careful. We have to do something that we haven't had to do before, and that's pay attention to the sign. I've worked the previous example, everything was in the same direction. Everything was down, so we didn't really have to worry about whether to call things positive or negative. But in this case, we have an initial speed of the rock is up, 3 meters per second up. But the acceleration, 9.8 meters per second squared, is down. Because those are in opposite directions, we need to give them opposite signs. So what we should do is pick a direction to be positive. And it really doesn't matter which direction you pick. What does matter is that once you've picked, you stick with it. Okay, so for this problem, let's say up is positive. That means that v0, 3 meters per second up, will stay positive. But the acceleration, 9.8 meters per second squared, is down. We need to make it negative. Okay? Now, what else do we know? Well, we know the displacement of the rock. When it lands, it's 10 meters lower than it was when we threw it. So the displacement is 10 meters, but once again, that's got to be negative because it's 10 meters down from where we threw it. Those are the things that we know. The things we're looking for would be v, the speed just before landing, and the time. So we need to pick a kinematic equation to solve for v. The third kinematic equation, v squared equals v0 squared plus 2a delta x, will work to solve for v. Let's plug in what we know, paying attention to the signs. v0 is 3 meters per second. That's squared, plus 2. A is a negative 9.8 meters per second squared, and delta x is a negative 10 meters. V squared is then, let's see, 3 squared is 9. That would be 9 meters squared over seconds squared, plus 2 times 9.8 is 19.6 times another 10 is 196. 196 also meters squared over seconds squared. Notice that the two negatives, the negative 9.8 and the negative 10, cancel each other out and become positive. So we have that v squared is equal to 205 meters squared per second squared, or v is equal to the square root of 205. I'm running out of room here. The square root of 205, we'll have to do that on our calculator. Square root 205 is 14.3. I'll write the answer down up here because we're running out of room down at the bottom. So v is equal to 14.3 meters per second. Okay, I'm going to clear the bottom of the screen, so again, pause if you need to write down what's at the bottom, and then continue when you're ready to keep going. So we found the velocity, we need to find the time. We can use before we do find the time, there's actually something that we need to address before. Let me rewrite that last step because we really ran out of room down there. We had v squared equals 205 meters squared per second squared, which means that v is equal to the square root of 205 meters squared per second squared. And if you remember from math class, actually, you'll realize that this could either be positive or negative square root of 205 meters squared per second squared, or v is equal to positive or negative 14.3 meters per second. So we need to decide which one of these should we use. Well, in math class, both of those solutions are fine. 14.3 meters per second, either positive or negative. In physics, though, we demand not only that the number make mathematical sense, but that it make physical sense. So, if I throw a rock up into the air, and then it goes down and lands 10 meters lower than where it was when I started, when it lands, should it be going up or down? Well, obviously it needs to be going down. And since we have defined up as being positive, if I want the velocity of the rock to be going down when it lands instead of up, I need to choose the negative root of this square root. So the proper velocity of the rock just before it lands is negative 14.3 meters per second. And we'll put that right here. Okay, now we're ready to find the time. We can use the kinematic equation v equals v0 plus at. Because we know v, it's negative 14.3 meters per second. That's equal to the 0, which is a positive 3 meters per second, plus a, which is negative 9.8 meters per second squared, times t. Okay, I need to subtract 3 meters per second from both sides. That gives me minus 17.3 meters per second equals minus 9.8 meters per second squared t. You need to divide both sides by negative 9.8 to get t by itself. So we'll do that on the calculator. We have 17.3 divided by 9.8, and that gives us about 1.77 seconds. 1.77 seconds. The time that it takes the rock to go up into the air and fall back down 10 meters lower than where it started is just under 2 seconds. And that's the end of this mini tutorial.